Alice and Bob take turns picking up whole piles of stones from either end of the row, with Alice going first, and each of them always tries to end up with more stones than the other. There's an even number of piles, each holding some positive number of stones, and the total is odd, so the game can never end in a tie. Egg advanced level, stone game, even pile count, odd total, take from either end. The claim is that first player is guaranteed a win under optimal play from both sides, not just favored, guaranteed for every valid input. That's a stronger statement than usually wins, so the proof matters as much as the algorithm. This is the canonical two-player interval game, identical shape to predict the winner and the ancestor of stone game 2 and 3. The interval DP over a zero-sum game pattern generalizes far beyond piles. Anything with optimal adversary picks from a shrinking range reduces to this. Piles 5, 3, 4, 5, both players minimax. Note this is a perfect information, zero-sum, alternating game with no hidden state. That's exactly the structure that lets us simulate both players into a single player optimization over a gap. This is interval DP. State is a contiguous subrange, not a prefix. That's why the fill order runs by increasing length rather than row major. dpijj depends on dpi plus 1jj and dpij and dpij1, both strictly smaller intervals. So length order is the only order that guarantees dependencies are ready. Naive minimax recursion is O to sen because the same iij subrange gets revisited to different move orders. Take left, then right, and take right, then left both land on the same interval. That overlapping subproblem structure is precisely what memoization or bottom-up DP exploits. Without it, you are recomputing identical subgames exponentially many times. The reframe, since total is fixed and constant across the whole game, tracking my scores and their scores as two separate quantities is redundant. The game reduces to a single scalar, my score minus theirs, and each player just maximizes their own sign contribution to it. This is the standard zero-sum game to single value collapse, and it's what turns a two-player problem into a one-player DP. dpij is the optimal gap for whoever moves next on piles ij denote. It's not Alice's gap or Bob's gap specifically, it's the mover's gap, which is what makes the recurrence symmetric and lets both players share one table. dpijj, max pile cg, dpi piles 1 jg, piles gg, dpijg1. The subtraction is the whole trick. dpi piles 1 jg is the opponent's optimal gap once they become the mover. And from your perspective, their gain is your loss. So you subtract it rather than add it. This is minimax expressed as a single max with negation baked in, instead of an explicit min layer. Base case dpigpigpis, the lone mover just takes it. The dependency graph only ever points to smaller intervals, so any topological order works. Length ascending is simplest to code, but a memoized top-down recursion gets the same complexity with less bookkeeping if you prefer that style. Standard n by n table, diagonal seeded with the base case. Straight translation of the recurrence. Worth noticing, dp0 n mens and wens wens and mens and mens and mens wens and mens and e0 is a strict inequality by design. Lead code guarantees odd total, so a tie is impossible here. But if you reuse this pattern for Stone Game 3 or a variant without that guarantee, you would need or explicit tie handling. End to end, O into time and space. Trace confirms the table. dp0, 3p0 max 5, dp1 3p0 5, dp0 2p max 5 4, 5p4 bp0. Mank. Notice both branches tie at 1 here. That's a coincidence of this input, not a general property. Don't assume the two branches always agree. Run it on 3, 7, 2, 3 before continuing. Then check it against the parity shortcut 2 slides from now and confirm they agree. Row major fill order reads dpi plus 1j before it's computed for larger jp silent. Not a crash, so it's the nastiest of the three. Tracking raw running totals instead of the sign gap breaks the subtraction identity entirely, not just off by a constant. And range 2, n instead of range 2, n plus 1 silently drops the full row answer, returning a subresult that happens to often still be positive. Which makes this bug easy to miss on these problems. Easy inputs and only surface on these problems, easy to miss on these problems, easy inputs and only surface on YJD in establishing one just to the identity entirely. The invariant, Alice can force either all even indices or all odd indices by always mirroring her second move to the parity opposite, whatever Bob just exposed. Proof sketch. After Alice takes an end, the remaining array has both ends at the other parity. Whichever Bob takes, the new ends are back to Alice's original parity. So by induction, she keeps access to her chosen class every turn. Odd total forces one parity class strictly larger, so OD1 return true always. This is why lead code flags it as a tricks problem. The DP is the general technique. The parity fact is specific to these exact constraints and shouldn't be your first answer's original parity. So by induction, she keeps access to her chosen class every turn. Own to time and space for the DP. Trivially reducible to own space with a rolling diagonally fast. DBij only ever reads row I plus 1 and its own row. The parity trick is own but brittle. It depends on both even pile count and odd total holding simultaneously. Change either constraint, arbitrary pile count, or optimize a different objective as in Stone Game 3. And the invariant breaks, the DP is what actually survives those follow-ups. N2 collapses to a single comparison. The real edge case worth raising unprompted. What if the pile count were odd or the total could tie? The parity proof and the strict zero both fail, and you'd need the min space DP with explicit tie handling. Expect a follow-up here. Stone Game 3 lets you take 1, 2 or 3 from the front only, which kills the two-pointer symmetry and forces you back to a genuine 1D DP over suffixes. Two proofs of the same guarantee, the general interval DP that survives rule changes, and the OR1 parity invariant that's specific to this exact constraint set. Know which one you're being asked for. If the interviewer says prove it, they usually want the DP or the induction argument, not just the one-liner. Here's one for you. With an even number of piles, can the first player always guarantee a win no matter what the pile values are? Pause and take a guess. Think back to that odd even index trick before you answer. The answer is yes, always. The first player can force taking every odd index pile or every even index pile, and since the total is fixed, one of those two sums has to be at least half, so they never lose. Round 2, our DP fills a table of gap values for every possible slice of piles. What's the time and space complexity of that, roughly? Don't just count the piles. Count how many slices there are. It's O of n squared, both time and space. There are roughly n squared possible start n slices, and each one takes constant work to fill in using the two n's we already solved.